Okay, everybody, welcome back to Calculus. Today we're going to be doing chapter 1.6, which is calculating limits using the limit laws. But first you need to know your limit laws, so we're going to go over that really quickly. So first we have the sum or difference rule, the sum and difference rule of limits, which says that the limit as x approaches a, where a is some variable of f of x plus or minus g of x, that's going to be equal to the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. And you can assume that these limits exist, and for these future limit laws, c is a constant and a is some variable and n is some integer. So for this first limit law, it's also said as the limit of the sums is the sums of the limits, or the limit of the difference is the difference of the limits, basically. If you have a limit of something plus another thing, it's basically the limit of the first thing plus the limit of the second thing. Then our second law says the limit as x approaches a of c times f of x, where c is some constant, that's going to be equal to c times the limit as x approaches a of f of x. So you can just bring that c to the outside, basically. Then we have the product rule, or the product property. It says the limit as x approaches a of f of x times g of x is the limit as x approaches a of f of x times the limit as x approaches a of g of x, which is similar to the sum and difference rule. This just says that the limit of the products is the product of the limits. Then we have the quotient property, which says that the limit as x approaches a of f of x over g of x is the limit as x approaches a of f of x over the limit as x approaches a of g of x, which is basically saying that the limit of the quotient is the quotient of the limits. So you can see a pattern emerging here. Then if we go over here, the limit as x approaches a of c is just going to be equal to c. And that makes sense because c is a constant. That's like saying the limit as x approaches 5 of 1 is going to be equal to 1, because it's just 1, it's a straight line. It's just going to be approaching 1. Then we have the limit as x approaches a of x equals a. So like the limit as x approaches 5 of x, well, if x is just x and it's approaching 5, then it's going to be equal to 5. The limit is going to be equal to 5. Then we have the limit as x approaches a of x to the n, x raised to the n, and that's going to be equal to a to the n, and n is going to be a positive integer. And so similarly, we get the limit as x approaches a of the nth root of x is going to be equal to the nth root of a. So that makes sense. It's just like this. It's kind of like the inverse of the exponent rule right there. And then we also have the limit as x approaches a of f of x to the n is going to be equal to the whole limit raised to the n. So those are your properties of limits. So there are a couple more properties of limits that I want to go over before we get to some practice problems. The first one is this property, which is similar to the other one we saw dealing with nth roots, but this one is dealing with the nth root of a function, whereas the last one was dealing with the nth root of x. So this says the limit as x approaches a of the nth root of f of x is going to be equal to the nth root of the entire limit as x approaches a of f of x. And then we get to the direct substitution property, which says if f is a polynomial or a rational function and a is in the domain of f, then you can just substitute that a value into that f of x function. So for example, let's say you're trying to find the limit as x approaches 2 of x plus 2. X plus 2 is a polynomial function. It's a first degree polynomial. So you can just directly substitute that 2 in for x, and you get 2 plus 2 equals 4, and that would be your limit. And then we get this other property which says is if f of x is less than or equal to g of x when x is near a, except possibly at a, and the limits of f and g both exist as x approaches a, then the limit as x approaches f of x is less than or equal to the limit as x approaches a of g of x. And I drew this graph here to kind of help illustrate it. So I have this a value, which I've marked off with an asymptote, and I have this g of x, which is this crazy wavy function. And you can see that at all points on the graph it's greater than f of x. So you can see that because of this, as the two functions approach the same a value, the limit for f of x as x approaches a is going to be less than the limit as x approaches a of g of x. And this this property kind of paves the way for the next property I'm going to talk about, the last property I'm going to talk about for limits, and it's a very important one. It's called the Squeeze Theorem. This is a very important property for limits and one you're going to want to memorize. This says if f of x is less than or equal to g of x, and g of x is less than or equal to h of x, when x is near a, except possibly at a, and the limit as x approaches a of f of x and the limit as x approaches a of h of x are the same L value, then the limit as x approaches a of g of x is the same L value. And that probably sounds very confusing, so I drew this graph out here as well. I've got this a value marked off here, and you can see h of x is greater than f of x and g of x at all points on this graph, and you can see f of x is less than g of x and h of x at all points on this graph, but at a, h and f approach the same value. So that forces g of x to be squeezed between them and forces it to basically have the approach the same L value. That's basically what the squeeze theorem is saying. It's if you have three functions and one of them is greater than the other two and one of them is less than the other two, then that middle one is going to be kind of sandwiched between those two functions and will approach the same value, or its limit will be the same as the other two at a given value. So those are your properties of limits. Now it's time to move on to some example problems. Okay, so in this question we're told the limits of three functions. We're told the limit as x approaches 2 of f of x equals 4, the limit as x approaches 2 of g of x equals negative 2, and the limit as x approaches 2 of h of x equals 0. And it says find the limits that exist. If the limit does not exist, explain why. So I'm just going to take this step by step. So in part A, we're asked to define the limit as x approaches 2 of f of x plus 5 times g of x. Well, recall that the limit of the sums is the sum of the limit. So I'm going to rewrite this as the limit as x approaches 2 of f of x plus the limit as x approaches 2 of 5 times g of x. And now remember from your constant multiple property that you can just move this 5 out here because it's just a constant. So we know that the limit as x approaches 2 of f of x is 4. So this is going to be 4 plus 5 times the limit as x approaches 2 of g of x, and the limit as x approaches 2 of g of x is negative 2. So it's going to be 4 plus 5 times negative 2, which I'll just write like that. So that's going to be 4 minus 10, which is negative 6. Then in part B, we're asked to find the limit as x approaches 2 of g of x cubed. And now remember from your exponent property that when you raise a function and try to take the limit of it, what you're going to want to do is raise the entire limit to that power. So this is going to be the limit as x approaches 2 of g of x, and this whole thing will be cubed. So the limit as x approaches 2 of g of x is negative 2. So we have negative 2 cubed, which is just negative 8. Then in part C, we're told to do the limit as x approaches 2 of f of x. Now, what I'm going to do is I'm going to put the whole limit underneath the square root sign. And if you're confused on why you do that, I'll just try to do this little thought process, this thought example here. Taking the square root of something is the same thing as if I had said f of x raised to the 1/2. Raising this function to the 1/2 is the exact same thing as taking the square root of it. And we know from our exponent rule that if we try to take the limit of a function raised to a power, we just raise the whole limit to that power. It's exactly what we did in part B. So doing that, I would have the limit as x approaches 2 of f of x all raised to the 1/2, which would just be the square root of the entire limit. And we know that the limit as x approaches 2 of f of x is 4, so it's the square root of 4, which is just 2. And then in this one, we have the limit of x approaching as x approaches 2 of 3 times f of x over g of x. So this one is going to be a little bit more intensive. We know from our quotient property that this is going to be the limit as x approaches 2 of 3 times f of x over the limit as x approaches 2 of g of x. This 3 is going to move over here because it's a constant, and we can write this as 3 times the limit as x approaches 2 of f of x, and the limit as x approaches 2 of g of x is -2. So then we have 3 times the limit as x approaches 2 of f of x is 4. We have 3 times 4 over -2, which is 12 over -2, which is -6. And that would be your answer for part D. And in this one, we have the limit as x approaches 2 of g of x over h of x. So I'm going to rewrite this as the limit as x approaches 2 of g of x over the limit as x approaches 2 of h of x. The limit as x approaches 2 of g of x is -2, and the limit of x approaches 2 of h of x is going to be 0. So this is going to be undefined, meaning the limit does not exist, which you can abbreviate as DNE. Now, in this last part, we're asked to find the limit as x approaches 2 of g of x times h of x all over f of x. So this is going to be the limit as x approaches 2 of g of x times h of x over the limit as x approaches 2 of f of x. So this is going to be the limit as x approaches 2 of g of x times the limit as x approaches 2 of h of x, and the limit as x approaches 2 of f of x is 4. Then the limit as x approaches 2 of g of x is -2, and the limit of x approaches 2 of h of x is 0, and that's going to be 4, or 0. So what we have is -2 times 0 over 4. -2 times 0 is just 0, so we have 0 over 4, which is just 0. Okay, so in this next problem we're asked to evaluate the limit, and the limit we're given is the limit as x approaches 3 of 5x cubed minus 3x squared plus x minus 6. Now, what you're going to want to remember for this is the direct substitution property, which says if you have a rational or polynomial function and you're trying to take the limit of it, you can just directly substitute the limit into the problem. Because I know from this we're not going to get like some sort of not real answer or an undefined answer. So I'm going to just directly substitute the 3 wherever I see x. So I'm going to have 5 times 3 cubed minus 3 times 3 squared plus 3 minus 6. 3 cubed is 27, so I have 5 times 27 minus 3 times 9 plus 3 minus 6. Well, 5 times 20 is 100, and 5 times 7 is 35, so you add those two together, and that's 135, but I will do it on a calculator just to double check. 5 times 27 is 135, 3 times 9 is 27, plus 3 minus 6. 135 minus 27 is 108, so we have 108 plus 3 minus 6. 108 minus 6, I'm doing that because it's just easier to do for me in my head, and addition and subtraction are commutative, meaning I could do these in any order. 108 minus 6 is 102. So we have 102 plus 3, which is 105. So that would be your final answer. Okay, so in this next question, we're given the exact same instructions, except we're asked to take the limit as t approaches negative 2 of t to the fourth minus 2 over 2t squared minus 3t plus 2. So again, this is a direct substitution problem. So I'm going to have negative 2 to the fourth minus 2 over 2 times negative 2 squared minus 3 times negative 2 plus 2. Negative 2 to the fourth is positive 16, so that's 16 minus 2 over negative 2 squared is going to be 4, so we have 2 times 4, and then negative 3 times negative 2 is positive 6, so that's going to be plus 6 and then plus 2. 16 minus 2 is 14, 2 times 4 is 8, so we have 14 over 8 plus 6 plus 2. So that's going to be 14 over 16. And you can divide both the numerator and the denominator by 2. And that's going to give you 7 over 8, 7/8. And that would be your simplified final answer. Okay, so in this next question we're asked to evaluate the limit, and the limit we're given is the limit as x approaches 8 of 1 plus the cube root of x, all of that times the polynomial 2 minus 6x squared plus x cubed. So this is another direct substitution problem, so I'm just going to do 1 plus the cube root of 8, that term times 2 minus 6 times 8 squared plus 8 cubed. So the cube root of 8 is 2, so it's 1 plus 2 times 2 minus 6 times 64, because that's 8 squared, plus 8 cubed, which I don't know off the top of my head, so I'm going to use a calculator to find that as 512. So that's 3 times 2 minus 6 times 64 would be 384 plus 512. So that's 3 times negative 382 plus 512. And 512 minus 382 is going to be 130. So we have 3 times 130, which is 390. And that would be your final answer. So in this next question, we're once again asked to evaluate the limit, and once again this is a direct substitution problem. So I'm just going to plug in 2 wherever I see x. So this is going to be the square root of 2 times 2 squared plus 1 over 3 times 2 minus 2. So 2 squared is 4, so it's 2 times 4 plus 1. 3 times 2 is 6, so 6 minus 2. 2 times 4 is 8, so it's the square root of 8 plus 1 over 4. That's the square root of 9/4. And if you remember your square root rules, this is the same thing as the square root of 9 over the square root of 4. So that's just 3/2. Okay, so in this next question we're asked to evaluate the limit if it exists. And we're given the limit as x approaches 5 of x squared minus 6x plus 5 over x minus 5. Now, if we just did direct substitution, we would get a number over 0, which is undefined, and we don't want that. So what we can do is we can factor out the numerator. That's the first thing I notice, is the numerator is factorable. So I'm going to make this limit as x approaches 5 of x minus 5 times x minus 1, because negative 5 and negative 1 multiply to 5 and add to negative 6, and that's going to be over x minus 5. Then this x minus 5 and x minus 5 are going to cancel out, so I'm going to have the limit as x approaches 5 of x minus 1, and now I can just directly substitute the 5 in for x and get 5 minus 1, which is 4. Okay, so in this next problem we're asked to evaluate the limit as x approaches 5 of x squared minus 5x plus 6 over x minus 5. So we have a very similar problem to the last one, but we're going to get a very different answer. So you'll notice that the numerator is still factorable like the last one, but when we factor it out, what we get is, what would we get for this? We'd get two numbers that add to 6. We'd get x minus 3 and x minus 2. These numbers multiply to positive 6 and add to negative 5, and we'd get that over x minus 5. Well, this doesn't really help us out that much. We can't cancel anything out. So what I'm now suspicious of is, well, what if there is no limit at all? So I'm gonna check the limit as x approaches 5 from the left. So it's gonna be a number slightly smaller than 5. Let's say 4, for example. 4 minus 3 would be a positive number. 4 minus 2 would be a positive number. A positive times a positive is a positive. But 4 minus 5 is a negative number. So it's a positive over a negative. So we'd have a negative number, and we'd be getting more and more negative as we approach 5. So the limit as x approaches 5 from the left is going to be negative infinity. And the limit as x approaches 5 from the right. So we're going to be plugging in numbers that are slightly larger than 5. So like 6, for example. 6 minus 3 is a positive number, 6 minus 2 is a positive number, and 6 minus 5 is a positive number. So it'd be getting more and more positive as we approach 5. So we see that it's negative infinity and infinity on either sides of the asymptote here. Well, we know that from our definition of a limit cannot exist here because the two-sided limit does not exist. So your answer for this is going to be DNE, does not exist. Okay, so in this next question we're asked to evaluate the limit if it exists, and we're given the limit as h approaches 0 of negative 5 plus h squared minus 25 all over h. So you can't use the direct substitution here because you'd get 0 on the denominator. So instead what I'm going to do is I'm going to expand negative 5 plus h squared and write it as negative 5 plus h times negative 5 plus h, because that's what negative 5 plus h squared is. Then I'm going to FOIL it out. So negative 5 times 5 is 25. Negative 5 times h is negative 5h. H times negative 5 is negative 5h. And h times h is h squared. And this can be simplified into 25 minus 10h plus h squared. Now we can write that back over here as the limit as h approaches 0 of 25 minus 10h plus h squared minus 25 over h. And this 25 and this negative 25 are going to cancel, giving us the limit as h approaches 0 of negative 10h plus h squared over h. And we can take out an h from each term here. So this h is just going to be a 1, this h squared is just going to be h, and this h is just going to be 1 as well. So that gives us the limit as h approaches 0 of negative 10 plus h. And at this point we can use direct substitution, and that's going to be negative 10 plus 0, which is just negative 10. Okay, so in this next question we're asked the exact same thing, but this time we have the limit as x approaches negative 2 of x plus 2 over x cubed plus 8. Now we can't use direct substitution here because we'd get 0 over 0. So what you have to remember here is that 2 cubed is 8. Once you see that, you'll realize that this denominator is the sum of the perfect cube. And we know that to factor the sum of the perfect cubed is this. If we have a cubed plus b cubed, which this is essentially x cubed plus 2 cubed, that's going to be equal to a plus b times a squared minus ab plus b squared. So when I go to factor this, I'm going to have the limit as x approaches negative 2 of x plus 2 over a plus b, so that's going to be x plus 2, and then a squared, so that's x squared, minus ab, so that's minus 2x, plus 2 squared, so 2 squared is 4. Now if I were to FOIL out this whole thing, I'd find that it's equal to x cubed plus 8. But right now I can cancel out these x plus 2's, and I'm left with the limit as x approaches negative 2 of 1 over x squared minus 2x plus 4. And now I can use direct substitution and plug in negative 2 wherever I see x. So that's going to be 1 over negative 2 squared minus 2 times negative 2 plus 4. So negative 2 squared is 4, and negative 2 times negative 2 is 4. So I have 1 over 4 plus 4 plus 4. Well, 4 plus 4 is 8, and 8 plus 4 is 12, so this is 1 over 12. Okay, so in this next question we're once again given the exact same instructions, but this time our limit is the limit as h approaches 0 of the square root of 9 plus h minus 3 over h. So once again, if we try to do direct substitution right now, we're going to have 0 in the denominator, which we don't want. So what you want to do every time you see a square root like this you're going to want to multiply by the conjugate. If you see a square root plus or minus some number, you want to multiply by the conjugate. And what the conjugate is it's the exact same thing you see here, except you just change the sign. So it's the square root, the conjugate of this would be the square root of 9 plus h plus 3. And we're going to multiply by the conjugate in the numerator and the denominator. So we're going to get 9 plus h plus 3 over 9 plus h plus 3. When we go to multiply this, 9 plus h times 9 plus h, the square root of 9 times the square root of 9 plus h, then square root is going to cancel out, and we're just going to be left with the limit as h approaches 0 of 9 plus h, and then negative 3 times positive 3 is negative 9, so 9 plus h minus 9, and then we're going to have h times the square root of 9 plus h plus 3. So these 9s are going to cancel out, and that's going to give us the limit as h approaches 0 of h over h times the square root of 9 plus h plus 3. And now we can see that these h's cancel out here, and that's going to give us the limit as h approaches 0 of 1 over the square root of 9 plus h plus 3. Now we can do direct substitution, and I'm going to bring this over here. So I'm going to plug in 0 wherever I see h, so I'm going to have the square root of 9 plus 0 plus 3. Well, the square root of 9 plus 0 is just the square root of 9, which is 3. So I'm going to have 1 over 3 plus 3, which is 1 over 6. Okay, so now in this next question, again, we're told to evaluate the limit, and we're given the limit as x approaches negative 4 of 1 over 4 plus 1 over x over 4 plus x. So this one looks a little bit trickier, but essentially what it comes down to is you want to get common denominators in the numerator. So I'm going to multiply this fraction by 4 in the numerator and the denominator. And I'm going to multiply this fraction by x in the numerator and the denominator, which is going to give me the limit as x approaches negative 4 of x over 4x plus 4 over 4x over 4 plus x. Now I can combine these, so I'm going to have the limit as x approaches negative 4 of 4 plus x, which is just, it says here x plus 4, but you can, 4 plus x is the same thing as x plus 4 essentially. So it's going to be 4 plus x over 4x over 4 plus x. And now we need to remember that division is like inverse multiplication. So we're multiplying right now, we're dividing this fraction by 4 plus x over 1, which is this fraction. Dividing is the same thing as inverse multiplying, which means it's the same thing as multiplying over 1 over 4 plus x, like that. So I can carry this over here and say the limit as x approaches negative 4 of 4 plus x over 4x times 1 over 4 plus x. And I can see now that these 4 plus x's here cross reduce, giving me the limit as x approaches negative 4 of 1 over 4x And now I can do direct substitution. I can say 1 over 4 times negative 4, which is negative 1/16. And that would be your answer for this one.